Firmware Guy presents his overview of I2C protocol. Before we go over what is I2C, a quick detour into why I2C. We need to use I2C because the rotational gyro that I've selected for the Tricopter project has a SPI and an I2C interface. And in this slide deck, we're going to review, do a quick overview of the I2C standard. By no means complete. If you want to have a complete explanation, I encourage you to utilize the spec link I provided in my website. I2C is a de facto standard. It's been implemented in many different I2Cs. Requires only 2 lines beyond power and ground. SDA, the data line, and SCL, the clock line. It's a bi-directional interface, and it supports transfer rates up to 5 megabits and as low as 5 kbits. Each device is individually addressable, and you can support multiple devices as well as multiple masters on the same I2C bus. When you're trying to understand a new protocol, it's important to understand the terminology that's built around it. This is a slide that gives a quick review of the common I2C terminology that you'll find in both the spec and many data sheets. So the transmitter is the device which sends data to the bus. Receiver, the device which receives data from the bus. Master, the device that initiates a transfer, generates clock signals, and terminates a transfer. And the slave, the device addressed by the master. I2C is a relatively straightforward protocol. It has 2 signals, SCL and SDA, which represent the clock and the data. It's important to know from the hardware designer point of view and trying to interpret logic analyzer traces when the data is read. And very simply, the data is read when SCL is high. So data must be valid at that time. SDA is allowed to change whenever SCL is low. So the data being transmitted can change from a 1 to 0 as it is in this example when SCL is low. So now that I've explained there's a really simple rule, I'm going to have to give you the exception. Because there are only 2 signals in I2C, a lot has to be communicated via SCL and SDA. So around every data byte is a start and a stop, or a start and a start repeat. And the way those things are signaled is they violate the rule that I just gave you on the previous slide. A start is when SCL is high and SDA is transitions from high to low. And a stop is just the opposite. SCL is high and SDA transitions from a logic 0 to a logic 1. Start takes on a different meaning too. It also signifies to all the other masters that the bus is busy, and a stop signifies that the bus is free. If the master that currently has control of the bus wants to send a repeated start, he can signal that and keep control of the bus. Byte format for I2C is pretty straightforward. Every byte on the SDA line is 8 bits in length. There is no limit to the number of bytes that can be sent in a transaction. Each individual byte is followed by an acknowledge bit, aka the 9th bit. During the acknowledgement, the master releases the SDA line. In other words, there's a weak pull-up. The slave can then pull the line low, an ACK, or allow the line to stay high, that's a NAC. If the master detects that a NAC has been sent by the slave, he can send a stop to abort, or can send a start to begin a new transaction. The first byte is preceded by a start or start R. This is a graphic representation of the slide I just discussed. On the left, you can see a start bit, followed by 8 bits of data, and a 9th bit that's either an ACK or a NAC. It goes from MSB on the left to LSB on the right, and The 8 bits of data plus 1 bit of NAC is repeated as necessary, and it's either followed by a stop or a start R if the same master wants to keep control and start a new transaction. The first byte of any transaction is used to specify the target device that the master wants to talk to, or the slave more properly. Sorry, my SCSI background comes through. The first byte of the start contains the address of the device, and then a bit that signifies whether it's a read or a write, or as I prefer, I think it's clear, referring to as in or out relative to the master. So a data in would be a read, and a data out would be a write to the slave. Let's quickly review a single byte read and a multiple byte read from my 4200D radial accelerometer. So if we look at the single byte transfer sequence, it has a start followed by a slave address plus a write. And my slave address happens to be 105 decimal, which is 69 hex. But when you see it in a trace, remember it's going to be shifted left once because it's in bits 7 through 1, and the read-write bit is bit 0. So the slave address plus write is followed by an ACK. Then the master sends the sub address. So this is the register that the master is interested in. Followed by an ACK, followed by a start repeat, followed by a slave address plus a read. So when we go over the trace in a couple of slides, you'll see the difference between a read and a write. Followed by an ACK, followed by the single byte of data from the slave, followed by an NMAC. Because of the vagaries of hardware and the fact that it's the last byte, the master never sends an acknowledge. The signal's always high, whether the data is true or not, or data is correct or not, followed by a stop. Transfer. This next example is for a multiple byte example, and it's very similar to the previous one. So we send a start, slave address plus the write signified, followed by an ACK from the slave, the address, in other words the sub, the address we're interested in on the slave, followed by an ACK, followed by a start repeat, and now it's the slave address plus a read, followed by an ACK from the slave, the first data byte followed by an acknowledge, next data byte followed by an acknowledge from the master. Actually, all these acknowledges are from the master. And then the last data byte followed by a NMAC followed by a stop. Let's quickly review the steps the master takes to send single and multiple bytes to the slave. In the first one, let's look at the single byte transfer. So the master sends an ST, which is a start, followed by the slave address plus a write. Remember, this is a 105 in our case. The slave will acknowledge. The master will then send the sub address or register he's interested in. The slave will then acknowledge that, followed by the data from the master. The slave will ACK that, followed by stop. Sending multiple bytes is very similar. All starts with a start, slave address plus a write, a slave acknowledge, the sub or address that the master intends the data to land at, followed by excuse me, an ACK from the slave, followed by the first data byte, followed by an ACK, followed by the second data byte, followed by an ACK, and a stop. Let's quickly review an actual trace of the transfer from my radial accelerometer. In this case, my part's address is 105, and we're going to read register 28, and we're going to use an option that this particular part presents, is that you can, with successive reads, read incrementing addresses if you set the correct options. So here is a write to device 105 decimal, and if you take this, you're going to see, remember it's the upper bits. Bits 1 through 7 are the address of the device, and bit 0 is whether it's a read or a write. So in this case, it's a write to device 105 decimal, and the slave sends an ACK. Then we're going to tell the slave we're interested in register A8. Well, it's not register A8 really, it's register 28 actually, with the uppermost bit set. And this uppermost bit, bit 7, signifies whether the address is auto-incremented. Then we're going to send an ACK. The slave will, or the master will send a stop. Master will send a start. Now he's going to read from device 105. That's why this bit is set. Then the slave will send an ACK, and then he sends a series of 1, 2, 3, 4, 5, 6 data bytes, so 3 registers worth. And this is the NMAC, basically the last byte, even if it's valid, will not get ACKed by this master, followed by a stop. This is the actual logic analyzer trace that produced the previous slide. This particular open source logic analyzer can translate these signals and understands I2C and breaks it down. It makes it very easy to read in the form that I just presented. This concludes my brief overview of I2C. I mean, really, it's just a basic introduction. I highly recommend that you dig out the slide from my website, www.firmwareguy.net. I have all the docs there, and read the doc. It's actually an easy reading spec. And always, if you enjoyed my presentation and found it useful, please subscribe. And once again, all the examples and links to documentation can be found at my website, firmwareguy.net. Thank you. Bye-bye.